Okay, let's check out this problem regarding solubility and ion concentration. It says beaker X contains 50 milliliters of distilled water. Beaker Y contains 100 milliliters of 1 molar sodium chloride. So here we've got just water. Here we've got water and sodium chloride. So we've got sodium ions and we've got chloride ions, right? Then we're going to add some solid silver chloride to each of the beakers. After thoroughly stirring, some solid silver chloride remains at the bottom of each beaker, as shown above. Which of the following is true? And we're looking at silver ion concentration. Is there none in either of the beakers? Is it zero on both sides? Is there some silver ion concentration but the same amount in both beakers? Or is it greater in X or is it greater in Y? So, what do we know about silver chloride? We know that silver chloride is a water-insoluble compound. When we first learned about solubility of ionic compounds, we learned that some are insoluble, and silver chloride is one of them. But later on, once we start to learn about solubility product constants, KSP, we realize that nothing is truly 100% water insoluble. Any ionic compound will dissolve even if to just a very, very tiny degree. Which is dictated by the KSP value. And so we know that silver chloride, AgCl solid, is going to be in equilibrium with the silver plus ion and the chloride ion. Right. This is going to be in equilibrium. And the KSP dictates which side dominates. Obviously, this has a very, very low solubility. So there's only a little bit of silver ions and chloride ions in solution. But now we have to look at the difference in the solutions, right? What's very important about the difference of these solutions? This is just water, so the KSP will dictate the ion concentrations, and there's nothing more to talk about. But here we also have chloride ions, right? We have sodium chloride. That's completely water soluble, so we have tons of chloride ions in there. And remember, we have to recall the common ion effect here, right? The common ion effect is a manifestation of Le Chatelier's principle, because what we're saying is sodium chloride has an ion in common with silver chloride, the chloride ion. And so what that means is that we have additional chloride ion. And from Le Chatelier's principle, we know that if we have more of one of these, right, it's as though, right, we're adding additional chloride to the solution. So whatever this equilibrium would be doing in pure water, now we have extra chloride from the sodium chloride. And if we have more product, Le Chatelier is going to tell us that is going to shift the equilibrium to the other side. In this case, to the left, to sodium chloride. And so what we're saying here is that the common ion effect, the presence of this common chloride ion promotes precipitation, right? So compared with just silver chloride in water, whatever that equilibrium would look like, the presence of additional chloride ion pushes the equilibrium back towards solid, which means that there's going to be even less silver ion and chloride ion concentration than would be the case in pure water, right? Because you've got more chloride that promotes precipitation. You need a silver ion and a chloride ion to join the lattice. And so what we're saying here is that beaker Y is going to have less silver than we would expect from pure water because of the presence of the chloride ion. So here we're saying that the silver ion concentration is greater in beaker X, where the common ion effect is not occurring. Right, so the key thing here was remembering the common ion effect, what it means in terms of Le Chatelier's principle, we're applying to this particular equilibrium with silver chloride and its respective ions, and then being able to use that to talk about ion concentration. Okay, let's try a question regarding equilibria, specifically involving gases. Here's a diagram that represents a mixture of NO2 gas and N2O4 gas in a 1 liter container at a given temperature. The two gases are in equilibrium according to this equation. Which of the following must be true about the value of the equilibrium constant for the reaction at this temperature? So we have some options for K. K is 0, K is between 0 and 1, K is 1, K is greater than 1, or we can't know. So what are we going to do here? First of all, if we want to know about the equilibrium constant, we should be able to write the equilibrium constant expression, right? So we definitely need to be able to do that. Once again, it's not very hard. We know that this is going to be equal to products raised to the power of their stoichiometric coefficients over reactants raised to the power of their stoichiometric coefficients. So the product is N2O4. So we're going to have concentration of N2O4, and its stoichiometric coefficient is 1, so there's no exponent. Over, there's only one reactant as well, and that is NO2. And that has to be raised to the power of its stoichiometric coefficient, which is 2. So this has to be squared. Now, the interesting thing here, and in general the interesting thing about the AP exam, is that they like to give you these situations where it seems confusing because you're not given quantitative data, right? We don't have concentrations to plug in here, but they give you enough information to infer quantitative to make conclusions, quantitative conclusions, because we have this drawing here and we can count these up. And yes, maybe in the 1 liter container there's not literally 3 molecules and 6 molecules, right? But these are, right, when we're talking about concentrations, we're talking about moles, we're talking about relative amounts, we're talking about relative numbers of molecules. So we can use these numbers of molecules and plug them in, and we can get information that way. So let's just pretend that each of these represents a mole, right? Because if it's a mole and it's a 1 liter container, we'll get our concentrations that we can plug in there. And if we plug in concentrations, or at least numbers that obey the relative concentrations of these substances, we'll solve for K, right? So this says that the 2 white balls here is N2O4 and the black circle is NO2. So we need N2O4 on the top. We've got 3 of them. So let's just put a 3, right? K equals, we'll put a 3 up top, right? And we've got 6 NO2s. So let's put NO2 on the bottom, but that one has to be squared. 6 squared, right? So that is 3 over 36. Now, this works. We can talk about K in this way. So which one is it? It's not 0. It's not 1. It's not greater than 1. It is between 0 and 1, right? We don't even need to get this as a decimal, right? We can see that it is positive. It's greater than 0, obviously, but it's less than 1, right? 36 over 36 would be 1. This is less than 36/36, so it is less than 1. So that's all there is to it. So the key thing here is, obviously, if we cannot write the equilibrium constant expression, we cannot answer this question. We must be able to do this, and you will get plenty of questions where you need to be able to do this. So that's a very important skill to have. But then, just using the logic of these relative amounts, relative numbers, we can plug those in and we can get a value for K, and we can assess. We can see that it is between 0 and 1. So that's a great one regarding gas equilibria. Okay, let's try a problem that has to do with equilibria, equilibrium expressions, equilibrium constants. So we have this generalized equilibrium here. The reaction mixture represented above is at equilibrium at 298 K. And the molar concentrations are X is 2 molar, Y is half a molar, and Z is 4 molar. What is the value of the equilibrium constant for the reaction at 298 K? So we need to know how to write equilibrium constant expressions, right? We need to know how to write K equals, and so what do? These are always the concentrations of the products, or the product of the concentration of the products raised to the power of their stoichiometric coefficients over the product of the reactants. By product, I mean you multiply them together, right? The reactants raised to the power of their stoichiometric coefficient. So up top, we have to have Z, and that has to be cubed. So concentration of Z cubed, right? Products over reactants. Z cubed over X squared, and then just Y, because that is to the 1. That's not raised to any exponent. So this is quite straightforward. We're going to plug these in, and we're going to do the math, right? So we get 4 cubed over 2 squared times 0.5. So 4 cubed, 4 times 4 is 16, times 4 again is 64. This is all math we can do in our head, hopefully without a calculator. And then we have 4 times a half, so that's just 2, and so that's 32. So the main part of this question is just making sure that we know how to write equilibrium expressions, right? The way we get the equilibrium constant is this way, right? It's always the product raised to the power of their coefficients over the reactants raised to the power of their coefficients. So this is 2, 1, 3, right? We do use those when constructing these expressions. Then we just plugged them in, the values they gave us, did the math, we got 32. So that is the answer for that one. Okay, let's take a look at this problem. Here we are dealing with an equilibrium, and we're going to be looking at Le Chatelier's principle. So this says a 2-liter reaction vessel contains an equilibrium mixture of the system represented above. We've got nitrogen gas and hydrogen gas and ammonia. So those are all, that's an equilibrium there. The partial pressures of the components of the mixture at equilibrium are listed in the table below. So the partial pressure of nitrogen is 0.3 atmospheres, partial pressure of hydrogen is 0.5 atmospheres, and partial pressure of ammonia is 0.2 atmospheres. So which of the following is the best estimate of the total pressure of the system when the volume of the container is reduced to 1 liter at a constant temperature? So temperature stays the same. We had a 2-liter reaction vessel, and that is going down to 1 liter. That is being compressed. So what do we know about if there is a compression? What do we certainly know is going to happen to the total pressure? The total pressure of the system is going to go up, right? Pressure it has to do with the force exerted on the container by the particles. So if the container is smaller and the temperature is constant, so they're not moving any faster, they're going to be hitting the sides with a greater frequency. So the pressure is going to go up. Now, if Le Chatelier's principle says that when a stress is induced upon an equilibrium or is exerted upon an equilibrium, the system will move so as to relieve that stress. Now here, how is this system going to relieve some of that stress of the additional pressure? Well, what it can do is it can shift so as to favor the side with fewer gaseous particles. Now we have all gases here, so they're all gas. And we have 0.3 and 0.5 over here, and then 0.2 on the right. So there are more gaseous particles of reactant than of product. So if this equilibrium were to shift to the right, so as to use up some of the nitrogen and hydrogen and produce more ammonia, there are fewer moles of gas on the product side. So by shifting to the right, it is decreasing the amount of moles of particles in the system, which in effect will reduce some of that additional pressure. Now the question is how much? How much is that going to happen? Because we've got some options here. So the total pressure, is it going to be exactly 1 atmosphere like it was, is it going to be 1 atmosphere like it was before? Is it going to be between 1 and 2 atmospheres? Is it going to be exactly 2 atmospheres, or will it be greater than 2 atmospheres? So we're going to have to use some logic here. It was 1 atmosphere, and if no shifting were to occur at all, right? If it just compressed and the system was unable to shift to favor one side over the other, we would precisely double the volume, right? We know this from, if it was just an isolated ideal gas, a singular ideal gas, you cut the volume in half, you're doubling the pressure at constant temperature. So we know that it's not going to be 2, and it's not going to be greater than 2 either, because we know that the system is going to shift to alleviate some of that additional pressure. So if it couldn't do it at all, it would be exactly 2. So for it to be greater than 2 is completely nonsensical. For it to be exactly 2 would only make sense if this was not an equilibrium, if this was just nitrogen gas, right, just by itself. Then the pressure would double. We also know it's not going to stay. It's not going to stay at 1 atmosphere, right? It has to go up to an extent. It cannot alleviate all of the additional pressure. That doesn't make sense. But we know that it's gonna be somewhere in between 1 and 2 atmospheres, right? It would be doubled, but then it alleviates some of that. So we end up somewhere in between 1 and 2. We don't know exactly. We don't know the exact final amount because we don't have any numbers here. We're not being quantitative in terms of an equilibrium constant. So we don't need to do that, but we can just exercise some logic to know that it can't be double or more, and and it can't stay where it was. So in between 1 and 2 is where we're going to land, and so that's a little bit about Equilibria and Le Chatelier's principle as it applies to pressure. Okay, here's a quick question on Equilibria, on Le Chatelier's principle. Now, you'll see this set up quite a bit where we have some statements and we need to figure out which one of those, which one or more of those are true. So these can be a little tricky, 1 and 2, 2 and 3, but we can just take them one at a time until we're very confident. So which of the following changes to the equilibrium system represented above will increase the quantity of HI gas in the equilibrium mixture? So which of these will make this increase? So number 1, adding H2. Okay, so if we add H2, if that goes up, then from Le Chatelier's principle, we know that if we add some amount of some substance, the equilibrium will shift to the other side, so to use that substance up. So increasing that will shift things to the right, which means we will get more HI. So that works. Now let's get rid of that. 2, increasing the temperature. Okay, so we do have thermochemical data here. We know that delta H is greater than 0. This is endothermic. This is an endothermic reaction. So what that means is that it requires energy input. So we can think of heat as a reactant. We can put heat right here. So we can treat it essentially like one of the substances, right? And so if heat is on the left, and temperature increases, it's as though we're just adding more heat, and then to use up the additional heat, the system will shift right. So again, that one does work. So that's a good one too. Then number 3, decreasing the pressure. We're going to look at moles of gas exclusively here, and so we've got 2 moles of gas on the left and 2 moles of gas on the right, because there's a 2 right here. So one of these and one of these makes 2 of these. Now, because it's the same number of moles of gas on either side, changing the pressure is not going to change anything. It's not going to cause the equilibrium to shift one way or another. So if there were more moles of gas on one side than the other, then decreasing the pressure would shift the equilibrium towards the side with more moles of gas, so as to restore some of that lost pressure. But here, it's the same moles of gas on either side, so that is not going to do anything. So 3 is not true. So we're looking for 1 and 2 only, so that is going to be C. And that was a nice little review with Le Chatelier's principle.